What if I told you that it's possible to design a recirculating aquaculture system, RAS farm, in such a way that there are practically no pipelines, no pumps at all, and not a single plastic tank? Hello everyone, my name is Anton. I'm an engineer, and I've been building fish farming facilities for over 10 years. Anton, seriously, what are you even on over there? Are you completely out of your mind or what? That's what you might say. But in reality, such systems have been in operation for decades already. And for those who already know what I'm talking about, who are in the know and understand, you already realize that I'm about to tell you about a channel-type RAS farm. Be sure to watch this video until the end, because we're going to figure out whether this is some kind of miracle technology or just a foreign Wunderwaffe. So if you're interested, first of all, give this video a thumbs up. Secondly, don't switch away, and let's get started. Well, let's probably start with a bit of historical background. In fact, people started raising fish in long rectangular channels a good 100 or even 150 years ago. Who was the first? At this point, I think it's impossible to figure out. The Americans claim the credit for themselves, the Europeans say they absolutely disagree, and so on. But in reality, that's not the most important thing. The point is, this technology, for us personally, it came from Europe, and to be more precise, from Denmark, because Denmark has a large number of such farms. You know, I personally have been to many fish farming enterprises in Denmark, and I can confirm that they really hardly ever use the classic tank layout for recirculating aquaculture systems there. So in principle, why not? Danish channel system is a perfectly good name. And by the way, the Danish channel system of my own design, which I'm actually standing on right now, I designed about 6 years ago. So, what is a channel system? Let's figure it out. Well, a classic recirculating aquaculture farm usually has tanks, typically made of plastic and usually round. This is the most common system in our industry. Like in the country, they are connected to each other by pipelines and also connected to the water treatment system by pipelines and so on. A channel system is a large reinforced concrete reservoir, essentially a single pool in which both the fish tanks and the filters are installed. Everything is set up inside it. The tanks are separated from each other, as well as the water treatment chambers, simply by concrete partitions. In other words, the entire pool is just divided into different chambers, with concrete partitions connected to each other in a specific sequence. Then instead of pipelines, the water flows from chamber to chamber simply by overflowing. So, we have a single volume of water that simply moves between the separate chambers of this reservoir. This is what a channel-type RAS farm is. A pool, an elongated rectangular channel. At the end of this channel, special fecal traps are installed. Basically, these are cones. A metal rubber-coated plug with a cable is inserted into the cone. The feces settle at the bottom of the pool, gradually move toward this cone, and fall into it. At some point, when a large amount of sediment accumulates in it, the plug is pulled out. The water along with the sediment is drained into the sewer. The plug is put back in, and that's it. The system continues to operate. So this is a basic mechanical filtration, because otherwise a huge amount of suspended solids would accumulate at the end of the channel. And these fecal traps are exactly what remove that suspended matter. The second device is a drum microfilter. Well, probably for those who are at least a little familiar with the topic, the first unit people usually hear about is the drum filter. Yes, the drum filter. Here it is used, but more as an additional unit. So, what is a drum filter? Well, first of all, here it is only used in a channel configuration. There are no drum filters with housings here. As a rule, these are large filters made of stainless steel. That is, it's a frame, and a stainless steel drum is mounted on this frame. The drum is covered with a special mesh and sits on rollers. It is driven by an electric motor. Water flows through the drum filter from the inside and passes through the mesh to the outside. All the contaminants stick to the mesh. Typically, the mesh size is 40 to 60 microns. Contaminants stick to this mesh and the water flows out. At some point, when the mesh becomes dirty, the water level starts to rise. At this moment, the level sensor is triggered. It sends a signal to the wash pump. The wash pump turns on, supplying water under pressure to wash the dirt off the mesh. Meanwhile, the motor rotates the drum, so we rotate the entire drum, knocking off all the dirt. All the dirt goes down the drain, and our drum filter resumes operation, starting a new cycle. And that's how it operates in automatic mode. Let's move on. Biofilter with floating media. Well, again, this is a very well-known component. There are no particular nuances to it. Basically, it's a reservoir. A reservoir divided into chambers. It's divided into chambers by special perforated partitions. That is, it's a partition that lets water through but doesn't let the media pass through. As a rule, it's divided into either one chamber or several chambers. The whole thing is filled with water, the biomedia is added, this is a special plastic granule, and then the filter is started. So we supply air to the bottom of the filter, to the diffusers. The air bubbles through the water, the media is constantly in motion, and it becomes colonized by microorganisms that carry out nitrification of the water, that is, the removal of ammonium, nitrogen, and nitrites from the water, converting them into nitrates. Next is the submerged filter, a cascade of reservoirs, not just a single reservoir. In each of the reservoirs, a special false bottom made of stainless steel is installed, similar to the partition in the filter, with floating media. In other words, it's a stand, and the false bottom is welded on top of it. It lets water through, but doesn't let the media pass. On this false bottom, a layer about 1 meter thick of sinking media, or expanded clay, is laid. From this chamber, sludge drain pipes are let out, which pierce through the false bottom. Water enters the chamber from above, passes all the way through it, through the entire layer of media, and, diving under the false bottom, continues on for further treatment. At some point, this sinking filter becomes clogged and is shut off. An aeration system is installed underneath the false bottom, air is supplied there, and the air stirs up all the dirt. The dirt is drained into these drain pipes, and the filter is brought back online. That's it. The dirt is drained, the filter is clean, and it goes back to work. Next is the aeration field, which is a network of perforated pipelines connected to a blower. Their task is to carry out degassing. By supplying a large amount of air and bubbling the water, we blow carbon dioxide out of the water. So we provide a large amount of air and pipes. The perforated pipes can be installed anywhere, essentially in an existing channel, or a separate place can be made for them. And in this way, we perform a simple and straightforward degassing process. Water transfer. The airlift is used to transfer water. It lifts water to a small height, 30 to 50 centimeters at most. What is it? It is a deep shaft. The shaft is divided by a partition into 2 semi-submerged sections. The partition does not reach the bottom, leaving about half a meter. This is exactly the depth at which the diffusers are installed. The diffusers are connected to a special compressor. A large flow of air is supplied to these diffusers. Due to the reduced density of this air-water emulsion, it rises upward and new water, diving under the partition, replaces it. And so we have a continuous circulation process, a kind of U-shaped airlift, where water is constantly moving thanks to the air. Well, probably the alternative would be propeller pumps and a channel oxygenator. So, propeller pumps are basically a pipe with a propeller inside, like on a boat or a ship. On top, there's an electric motor that drives the propeller. So this pump is usually a vertical pipe that is lowered into the water. And it pumps large volumes of water, but only to a small height, 1, 2, 3, up to a maximum of 5 meters as a rule. And finally, there's the channel oxygenator. So when we need to saturate the water with pure oxygen, we use a channel oxygenator. This is a platform usually made of stainless steel with nozzles. It is submerged, also lowered into a shaft. Water is pumped from above by a propeller pump into this oxygenator. The column of water presses against this perforated plate. Water passes down through this plate via the nozzles and oxygen is supplied from below. As a result, jets are formed, spraying the water. They draw the oxygen along with them, the water mixes with the oxygen, and under slight pressure, everything mixes even more efficiently. Then the water, now saturated with oxygen, flows out and continues onto the fish farming tanks. Now let's talk about the pros and cons of the channel technology. Well, the first advantage is the ease of operation. Why do I like this system in general? Just imagine, we have a classic RAS, recirculating aquaculture system. Pools, pipes, water treatment tanks, all at different heights. Something can get clogged somewhere, something can overflow somewhere. I've seen a huge number of such problems in classic RAS systems. What's the beauty of the channel system? Here, there's nothing to overflow, nothing to burst, nothing to break. In other words, it's so simple that with a properly designed system and usually reliable equipment, it guarantees you success. So it's extremely simple to maintain, to operate in every aspect. Protection against failures. This is precisely a result of the fact that everything is located in a single reservoir, simply divided by partitions. So the likelihood of something bad happening here is much lower than in a classic tank system. High energy efficiency. Since we use low pressure pumps here, for example, propeller pumps, we don't have any special devices that create high pressure, as is often the case in tank systems, so on average, the energy efficiency of a raceway farm is higher than that of a conventional classic tank system. Well, it would be strange if this system didn't have any drawbacks. There are some main disadvantages. I see 2 of them. The first is the large amount of concrete work required. Just look here, for example. I'm standing in front of a farm that we built a couple of years ago. A huge amount of concrete was poured here. So, to make all these tanks, chambers, and overflows, you really need a lot of concrete for all of this. And it needs to be done with high quality. And the second drawback again is that since this is a large monolithic tank and involves a huge amount of concrete work, it generally isn't suitable for installation in existing buildings. Because first of all, you can't change its configuration. It's not like you can just move the pool over here or shift the filter over there. But that's not possible with a duct system. If it runs into columns or doesn't fit into the existing building, then sorry, it just won't fit there. And unfortunately, you can't adapt it as easily as a pool system. And another point, even if you manage to build it into an existing building, now you have to pour all that concrete. Can you imagine how much you'll need? The amount of manual labor, because it's almost impossible to bring in a concrete pump or any heavy equipment like excavators for earthworks. You have an enclosed existing building, so typically duct farms are built in new constructions. Let's talk about the basic calculations for designing a duct farm, starting with planting density. Here, it's no different from a tank system. Well, let's put it this way. If it's a simple system on an airlift, I wouldn't set the density too high. Stoking density above 50, well, 70 at most, if you also supplement everything with a separate oxygen circuit. But if we're talking about using pure oxygen with a channel oxygenator, then the density is exactly the same. For example, for trout, from 70 to 100 or even up to 120, again, provided certain principles are followed, particularly regarding water exchange and oxygenation. By the way, about water exchange. As for water exchange in such systems, I would recommend the classic standard for trout, not less than 3. And, by the way, for trout larvae, I would even go for 4 to 5 for larvae and fry. Channel volume. In fact, the channel volume here can be set to any value. That is, if we're talking about fry or larvae, I wouldn't make a channel. No more than 1 meter by 1 meter, in cross-section and about 5 meters long. That's the maximum I would do for larvae. If we're talking about market-size fish, then you can easily make it larger. 5 meters wide, 2 meters deep. 30 meters long, so for example, a large U-shaped channel like that, I don't see any problems with it. It's absolutely doable. Fecal traps are usually sized 1 meter by 1 meter by 1 meter, that is, width, length, and depth, and are installed at the end of each fish farming channel, covering the entire channel profile. Drum filter. A classic channel drum filter, definitely not a housing type filter. I would recommend one made of stainless steel so you don't have to reassemble it piece by piece later. At the first sign of problems, be sure to have a 30 to 40% performance margin. Never select a drum filter that just barely meets your needs. A biofilter with floating media. A standard biofilter with a water depth of about 1.70 meters, I recommend, with an aeration coefficient of 8 to 10 and with biomedia calculated for the total oxidative capacity of the entire system. Yes, absolutely, we also have a sinking filter, but ideally, the sinking filter should just serve as an additional safety measure. Well, at least 50-50. Half of the oxidative capacity is handled by your main biofilter and the other half by the filter with sinking media. And yes, now about the filter with sinking media. That is, its hydraulic load is 25 cubic meters per square meter per hour. This is how much water can be supplied to 1 square meter of the area of this filter. The thickness of the media layer is from 80 centimeters to 1 meter. That's my recommendation. It must be sinking media. If you have expanded clay instead of sinking media, then I recommend increasing the surface area of your filter. At least 2, or better yet 3 times, because expanded clay has a lower hydraulic load capacity. Aeration field ratio. Air to water ratio is 5 to 1. Diffuser installation depth is 70 centimeters. What else? I recommend using high pressure blowers for such tasks. Airlift. Water depth is 2.5 meters above the diffusers, total depth is 3 meters. Taking into account the dry reserve, airlift is 3.5 meters. The air to water ratio ranges from 1 to 1 to 1.5 to 1. Well, that's basically it. I've told you all the main nuances of the duct system. What it is, how it works, what equipment it consists of, we've discussed its pros and cons, and even covered the basic numbers for its calculation and selection. If you found this helpful, give it a thumbs up, subscribe to my channel and my Telegram channel, and I recommend watching this video. This was Anton with my channel about how to farm fish and make good money from it. Bye!